Why Spark jobs are slow? Let me start with a slightly uncomfortable truth. Most Spark jobs are slow. Not because Spark is slow, but because developers fight the engine. Spark is actually very fast by design. When jobs are slow, it's usually because how we write the code. Common reasons are too many. Shuffles, poor partitioning, excessive UDF usage, and memory pressure. In this video, we are not going to tune random configs. We are going to understand why Spark behaves the way it does. The real enemy of Spark performance is not data size. It's writing code without understanding execution. Many developers assume Spark behaves like Python, or they treat Spark as a black box. I'll write code and Spark will optimize everything. That's not how it works. Spark is fast only when you cooperate with it, not when you fight it. If you remember only one slide from this video, remember this one. There are three golden rules of Spark. Rule 1, minimize shuffles. Rule 2, stay inside the JVM. Rule 3, match partitions to parallelism. So everything you learn in video 1 and video 2 connects back to these rules. Now let's start with shuffles. A shuffle means data movement. Data move across the network, spills to disks, and moves between executors. This is expensive. The most important line to remember is this: every shuffle is the tax on your Spark job. The more shuffles you have, the more you pay in time, memory, and stability. Now let's talk about partitions. One of the most misunderstood concepts in Spark. Partitions are not files. Partitions are units of parallel work. One partition means one task. One task means one core doing work. If you have too many partitions, Spark spends time managing tasks instead of doing work. And if you have too few partitions, CPU sits idle. This is why I say Spark performance is often a partitioning problem. A common myth is that more partitions always mean faster jobs. That's not true. 100 partition is not automatically faster than 10. The ideal number of partitions depend on the data size, the available cores, and whether the stage involves a shuffle. Parallelism is useful only when there is work to do. Otherwise, it becomes an overhead. Let's zoom back into shuffles. During a shuffle, Spark does network input output, disk spills, serialization, and creates stage boundaries. This is where most Spark jobs slow down. And here's a key idea. If your job shuffles a lot, config won't save you. Good design beats tuning every single minute. Now, joins are one of the biggest sources of shuffles. Large table joining with another large table is expensive. When one data set is small, Spark can use a broadcast join and avoid shuffling the big table. But when both sides are large, Spark usually has no choice. That's why many small Spark jobs are actually slow joins. Now let's talk about something every Spark engineer has faced, that's data skew. Some keys have much more data than others. One task end up doing most of the work while others finish early. And here's the important line. If one task runs for 30 minutes, your job is slow, even if all others finish in seconds. This is why Spark jobs appear stuck at 99%. Now, caching is another commonly misunderstood feature. Cache is not free. Cache data occupies executor memory, and cache data must be reused to justify its cost. Caching a one time data frame or caching large data sets blindly often slow down Spark jobs. That's why the myth caching everything makes Spark faster is completely false. Caching helps only in specific cases. When the same dataset is reused multiple times, when an expensive computation is reused, or in iterative workloads like machine learning. A simple thumb rule is cache for reuse, not for hope. So let's come back to our golden rule. Spark's optimizer works inside the JVM. Built-in Spark functions are optimized, vectorized, and JVM native. Python UDFs break this pipeline. And this is extremely important. If Spark can't see inside your logic, it can't optimize. Built-in functions allow Spark to optimize execution. Python UDFs introduce serialization, remove catalyst optimization, and slow down execution. This is why replacing UDFs with built-in functions often gives massive performance gains without changing infrastructure at all. Now, configuration tuning. Configuration tuning matters, but only after a good design. Focus on the basics: executor memory, cores per executor, and default parallelism. But remember this: bad logic plus good configs is still a slow job. Let's end with a simple mental model that you can carry into every Spark job. Try less shuffle, more parallelism, and try to stay inside the JVM. If you do this consistently, Spark jobs will reward you. Think like Spark, not like Python. With this video, you can confidently answer questions like, why is my Spark job slow? How do I reduce shuffle? How do partitions affect performance? When should I cache data? Why should I avoid UDFs? Why do joins kill performance? So in the next video, we'll go deeper into Spark SQL, Catalyst, and AQE. Thanks for watching. See you in the next time.